Bismillahirrahmanirrahim and Assalamualaikum warahmatullahi wabarakatuh to the moderator, respected panels, SAIS committee and fellow presenters. My name is Nur Syuhada binti Amir and today I will present about my paper which entitled Resource Allocation Scheduling for Delay Optimization in 60 Terahertz Communication Using Deep Reinforcement Learning. First and foremost, I will introduce about the current issues and also future network issues. Going to the first issue is increases number of devices. Today, it offers numerous services, rapid growth in mobile traffic, particularly in densely populated regions. The new services mentioned here is that smart mobile device will offer services such as ultra high definition video, 3D video, virtual reality, augmented reality, and many more. NET is limited spectrum frequency band. Telecommunication providers limit the same radio spectrum frequency band. Each device is given a limited amount of bandwidth, resulting in slower speeds and frequent disconnections. Moving on to the next issues is higher data rate. As the number of users increases, so will the transmission rate, making the delay of each data rate critical. Last but not least, the issues is I mentioned here high frequency deployment. Current cellular cannot accommodate with future network requirement. High frequency deployment would cater the requirement. Reduction for the 60 performance requirements. So before I introduce the 60 requirements, we may flashback about the 5G requirements, which are URLLC, which is ultra reliable low latency communication, MMTC, massive machine type communication, and EMBB, enhanced mobile broadband. So we expected the new combinations of requirements for the new cases are required. So the 60 requirements are the improved requirements from the 5G, which is first extreme high data rate or capacity. So the peak data rate is expected to be more than 100 gigabit per second, exploiting new spectrum bands, and 100 more capacity for the next decade. The next requirement is extreme low latency, always low latency, which is end-to-end low latency with less than 1 microsecond. Next requirements in 60 are extreme coverage with gigabit per second coverage everywhere and new coverage areas. Next is extreme low energy and cost. So 60 is expected to have affordable millimeter wave or terahertz devices and devices free from battery charging. The next requirement is extreme high reliability, which is guaranteed QoS or quality of survey for wide range of use up to 99.999% reliability, secure, private, safe and resilient. Last but not least, the requirements are extreme massive connective. So massive connectivity devices which are expected that 10 million devices per kilometer square and sensing capabilities and high precision positioning. So when compared to 5G, these technologies are expected to bring a lot of new applications with impressively high requirements in terms of latency, reliability, energy efficiency, and capacity. These are the key enabling technologies that are essential to the realization of 6G. These key technologies are expected to achieve the remarkably 6G requirements in terms of latency, reliability, energy, and efficiency. The enabling keys are millimeter wave communication, terahertz communication, and optical wireless communication, which in this paper I decided to focus on the terahertz communication. With the exponential growth of the data traffic in wireless communication system, terahertz frequency band is envisioned as a promising candidate to support ultra broadband for future beyond 5G, bridging the gap between millimeter wave and optical frequency ranges. So the terahertz bands offer hundreds of gigahertz usable spectrum resources for wireless communication in long, medium, short, indoor or near field range. Next is the problem statement. So the issues here I highlight is evolution of technologies with different type of devices requirements leads to the higher data rates and capacity requirement. That will lead to use high frequency bands such as terahertz band due to the wider available bandwidth in these bands and ultra dense network to cater demands in the future. So the problem here is high frequency that lead to small coverage and increased density of users in the network will create delay issues in cellular network. So this will affect the network quality and performance, especially delay. Proposed method I propose is thus 60 terahertz band communication is expected to provide the solution for transmission delay. Terahertz communication use the 0.1 until 10 terahertz band, which has more abundant spectrum resources than the millimeter wave band. And The next method is efficient scheduling method may increase the energy efficiency, avoid data loss, and offer better quality of experience to the users. So, my research objectives are: first, to study the delay requirements of Terahertz communication technology in 6G cellular network. Next, to develop a resource optimization scheduling in Terahertz span communication and to adopt DRL method for efficient resource optimization. For the resource methodology, this project proposed a resource allocation scheme for wireless networks aiming at optimizing the user's data delay. It is proposed to provide optimal delay allocation by solving an optimization problem using ideal state prediction and considering 6G characteristics such as terahertz wave propagation. To make the research method more understanding, we can refer to this figure. This figure indicates my scheduling model at the base station or E node B. In the MAC layer, it contains a block of information such as queue size, HOL delay, service rate that are obtained from the buffer. Next, the scheduler will receive this information along with the QCI requirement and uses it to determine the flow of the scheduling way. As example, in delay-aware strategy, it will use HOL delay obtained from the buffer and information about the target delay to execute how resources should be allocated to the users. So, scheduling rules will use variety of ways to meet the end user's needs such as target throughput, packet delivery, delay bounds, the packet loss rate, or any combination of these. Portion is the flowchart of the scheduling model. It started from when the user equipment requests packets from base station and the packets queue in the buffer. Next, HOL is used to measure the packet delay and the base station will observe the queue length of each user equipment. So here the channel condition will update using the channel quality indicator. The CQI value will range from 0 to 30, which 30 indicates the best channel quality and 0 or 1 indicates the poorest channel quality. So if the network gets high CQI value from the user equipment, it transmits the data with larger transport block size and vice versa. So then it will get into the target delay valuation, which if it has more than 100 milliseconds, it will assign resource block, the packet will transmitted, and if it didn't exceed the 100 milliseconds, it remove the packet to the millimeter wave queue buffer. On to the relationship of deep learning and artificial intelligence. My focus in this paper is aiming to adopt a DRL algorithm to achieve my objective. Deep learning is a subset of machine learning from artificial intelligence. Meanwhile, deep reinforcement learning is one of the popular methods along with deep neural network. Moving on to the result and discussion. So this is the parameter table for the simulation, which I said the bandwidth is 200 kHz, which is the requirement for the terahertz communication. So the small cell radius is 50 meter and the number of devices I said here 10, number of iterations is 95,000. We conduct a simulation to evaluate performance of the proposed algorithm for 95K independent runs during the training process. So the performance of the DRL algorithm is evaluated in terms of loss Q function. In general, figure 6 shows that the loss of the Q function decreases as the number of iteration increases and has lowest loss function value after 95,000 training iterations. Success rate and the average number of transition steps are used to evaluate the performance of the algorithm. The success rate is calculated by dividing the total number of independent by the number of successful trials. If it goes to a desired state within 20 time frames, the trial is determined as successful. If a trial is successful, the average number of transition steps is defined as the average number of time frames necessary to reach a goal state. From this graph, we can observe that the analytical expressions for delay clearly shows the dependence on system parameters like SNR, number of antennas, and arrival rate of packets. We also observe that the delay is inversely proportional to the minimum of number devices. We observe that the delay increases with increases in the SNR due to the inverse relationship with number of antennas, which I said here is 20. We then examine the trade-off between the link wastage or throughput and the average waiting time shown in figure. So the link wastage here is defined as the fraction of time slots that are packets in the system, but the queue is empty and the link is available. From the result, we observe that if there are so many packets added to the queue and the link becomes unavailable, highly average delay will occur. On the other side, a measured approach that increases link wastage due to a shortage of packets in the millimeter wave queue is not ideal. As the figure illustrates, the largest reward is obtained for threshold 11, which is the same threshold value with zero link wastage as and the least average delay. For the future work, the proposed method can be quite general and flexible, as the reward function can be extended by jointly consider the effect of throughput, QoS requirements, latency, and parity. I leave this topic for the future investigation. Next, from the conclusion from this paper is the scheduling method is modeled to optimize the delay. We also adopt DRL algorithm back into the scheduler. The results show that the delay has improved in terms of the queue loss function over iteration and the delay over the number of devices. What makes DRL appealing is we can customize the reward function for a specific problem. In this paper, we directly use the negative value of the objective function as the reward function. So, maximizing the reward function will be equivalent to the minimizing the average delay of all user equipments. So, this is the list of papers that I used to cite for my slide and my papers. That's all from me. Thank you.